Today's lecture will be a continuation of the discussion of statistical methods in research, and this will be the first of two lectures from the Module 2 Lecture 9 PowerPoint or lecture file, and we're continuing with our discussions of research design and data management. And this lecture today, hit the wrong button there. This lecture today will cover the one-way analysis of variance, and then in lecture 9-2 we will continue to discuss analyses that include repeated measures, types of data. We will then discuss in the lecture 10 the two-way analysis of variance with and without a repeated measures. So before viewing this lecture, it's best that you view the lectures 6, 7, 8, and 8, I should say, to build up to this point of appreciating the descriptive statistics, the measures of central tendency, dispersion around the mean, how that is relevant, the calculations of the mean and variance and standard deviation, as well as standard error of the mean from the prior lectures. So we have an appreciation of what those are and have viewed the formula for those before we cover discussion of the formula and calculations for the one-way ANOVA. We also will use a flow chart to help make decisions based upon our experimental design of what statistical analysis would be important, and we'll see that over and over in the next few lectures. Basically, a one-way analysis of variance, or ANOVA, analysis of variance, is used when you have more than two treatment groups. And we will be talking about different factors and levels of factors and using such terminology as we proceed. And this is important in understanding experimental design from the perspective of statistics. We have said that statistics should come first in an experimental design, but we know that in practice we typically think our way through, reason our way through with our rationale as to how we want to perform an experiment. Then we begin to think about how we would test it statistically. And I recommend that it should be a circular format going in the process as I just described, but then once evaluating the statistics and what you might be able to do or not do with statistics, or just how complicated it might be, you might come back and reevaluate your design such that the data analysis, ultimately the statistical analysis as a part of your data analysis, is more straightforward and will contribute to the ease of understanding and interpreting your data in the end. So we're now considering ways to deal with comparisons of more than one data group. We talked about the student t-test, calculating the t-test statistic observed value, comparing it to the predicted value, the critical value on a table, for comparing two experimental groups, and the f-test for testing equal variances on two groups. We will now proceed to discuss the analysis of variance for when it's more than two groups, and a modified f-test, a Fisher test, will be similar, a ratio of the standard deviations, a ratio of the variances, but slightly modified because you have more than two treatment groups. Let's continue here then. Ways to deal with comparisons of more than one data group. When it exceeds two data groups, two treatment groups, then there is the risk for potentially elevating the false positive rate. So you may find a difference when one truly doesn't exist. So there has to be a more stringent way of testing the data, looking at the variance within the groups and across the groups to make sure that the variance that you see is due to the differences across your treatment groups and not within any one or more of your treatment groups. And this is basically what the analysis of variance will be. So there, you have to perform a global test for differences and only conduct a follow-up test to compare your different groups if the global test is significant. So in other words, if you have more than 2 treatment groups, 3, 4, 5, whatever it is, then you must pass the analysis of variance. In other words, the analysis of variance outcome must show a statistical significant value before you can go on to make any post hoc comparison of your treatment groups. It is not valid to compare the treatment groups without doing an ANOVA or after doing an ANOVA and the ANOVA is not significant. This is a strict rule, because you may find you can do the post hoc test and get comparisons and you have significant differences, but the ANOVA is not significant. So you cannot report any of the differences between your treatment groups as being statistically significant because you did not pass the ANOVA, meaning that you have a source of variance that cannot be explained based upon your different treatments. In other words, we begin thinking that within any one treatment group we've got this very low accuracy. It may be it may have a low bias. Your mean may represent the real population, but for some reason you have a low precision, a dispersion, a broad dispersion of your data away from the mean. And if that is the case, if that's a cause of variance, we know that we can go back and evaluate our confounding factors, potential sources of variation within that one experimental group to see what might be done. As you learned from Lecture 6, you can begin to exclude data after analysis or after collecting it and going through the first stages of the data processing. If you find that some of your data points satisfy the outlier method. So that becomes very important to process your data correctly, excluding data when justified before analysis and during analysis, and especially to control collection of data so that you have justified exclusion. You know, if all of your cells die or if the animal dies, whatever it is, during the experimentation, you obviously are not going to collect any data on that, so that's excluded and it's justified before you get to the data collection analysis stage. So you want to justify that before you finally collect your data and go into the initial processing phase. During the processing phase, basically the outlier method, or maybe where you have to test for normal distribution, or you might transform the data, some things like that, before you go on to the next phase of the evaluation. There can be some cycling in there within the data analysis, as you'll see in this discussion, but you need to accomplish as much of the let's say rectification of the data. I don't want to say cleaning up of the data because it sounds too purposeful, but it's rectification of it that you are excluding based upon justified approaches, valid approaches, and then you begin your data analysis. So with experimental design, we control bias and confound, all those matters that we discussed there, so that the outcome measures should be most reliable. Things may go wrong between the start and the finish of the actual experimental procedure, justifying exclusion of data or data sources along there. And then we saw the outlier as a valid and accepted method of excluding data in the initial processing phase. Once you've got your descriptive statistics for a normal distribution, any value that is plus or minus, greater than plus or minus 2, I should be saying greater than or less than, more than or less than 2 standard deviations away from the mean can be excluded before going on to any type of statistical test that ultimately will compare the different treatment groups. It's a lot of words, but it's a critical aspect of responsible conduct of research at the stage of data collection, data acquisition, data analysis. So employing a statistical procedure which takes into account the number of hypotheses to be tested and adjusts for it accordingly. So there are mathematical procedures that create a higher degree of stringency if you're making a large number of comparisons, if you have many hypotheses, statistical hypotheses that are being tested. So that you want in the end to have a statistically significant difference from the most stringent test, statistical mathematical formula applied as possible. Then you have the highest level of scrutiny and credibility in your data set. Your final conclusions can be drawn from those. So testing, so in other words, if you draw conclusions on questionable or faulty statistical approaches, then the data is, of course, discredited, disqualified, and disbelieved, right? So, nullified, another nice term to throw at it. So testing hypotheses in a sequential manner so that certain tests are only conducted if all previous ones are significant, such as the analysis of variance before doing post hoc tests to compare the different treatment groups. So some examples of these three approaches. The ANOVA is the one we're going to focus on. Here's a good time for me to tell you the obvious, that I'm obviously not a statistician. I don't see myself as an expert in statistical formulas and tests, but I have developed through many years of effort a level of appreciation of how we can utilize them, and I hope that I can share that level of familiarity of this information with you so that you feel good about the tests that you run on your data. You may be doing simply what is performed routinely in your laboratory, and hopefully these lectures will get you started in appreciating that, understanding why, being able to justify the statistical tests that you use in proposals and reports, research articles, whatever it may be. And then, if you really want to, you can take statistical courses and develop the level of expertise that you desire. But you do need, as a basic commitment to your responsibility, you do need a familiarity to a level that allows you to justify and defend your choice of statistical approach and thereby experimental design. So the ANOVA is quite common when there's more than 2 procedures. So the analysis of variance is that an example of a global test of group differences. Now, group here, we're using this term as treatment groups, but it's obviously 3 or more treatment groups in a one-way layout. So let's not worry about this too much right now, because we will make more sense of it when we talk about the 2-way ANOVA. This is when we start talking about different factors and different levels of the factors. So one-way layout or one-factor design is a term that is applied here. You have multiple treatment groups, but it's only one test factor that you are changing, altering at different levels. It might be different concentrations or variations or combinations of drugs, as we will see. So we'll try to work out some examples as we go along. And then followed by, if you successfully pass or establish statistical or a significant probability, or P Remember, we always set our P at less than 0.05. We set the same for the level of significance to pass our ANOVA. We may pass with greater, colors. That's not the term. Anyway, a higher degree of significance, 01, 001, 0001, whatever it is. But just so long as we're less than 05, we can satisfactorily accept that level of significance. At the 05, remember, you're accepting the risk of 5% false positives. So then you follow up after getting past the ANOVA with the pairwise t-tests. We'll talk about a few different types of tests. They're called post hoc tests. So they come after the analysis of variance. So after this fact, you then can make pairwise comparisons. Now, it is not widely accepted to use the student t-test to make the comparisons between your groups after getting past an analysis of variance, because it isn't of a high enough stringency. So there are other tests that through their formula, it's magic to me, but anyway, have punched the button on the computer program like many of us probably do. Through the design of the formula, a greater stringency, a greater difficulty is built in order to achieve a critical value that establishes significance. So if the overall ANOVA indicates significance, so the Fisher protected least significant difference test is one example. Again, we're not going to go through all of these in any level of detail. If you use them, you'll become very familiar with them. If you want to become an expert with all of them, go seek out the appropriate courses and study and practice. Next, for the multiple comparisons tests, there are several that are used: the Student-Newman-Cool's, Tukey's, Sheffay's, Tukey's and Sheffay's, Dunnett's or Dunn's tests, or using a Bonferroni adjustment for the number of tests conducted. So this is when you're testing multiple hypotheses. You want to make a correction with your data sets so that it is more difficult to establish significance. You've stepped up the level of stringency. So we're always correcting to minimize our errors, the type 1 and the type 2. Remember that. For these up to the Dunnett's, we have an increasing level of stringency for these examples of post hoc multiple comparison tests for significance between the groups. You typically will decide how you want to go about this. The Dunnett's and Dunn tests are typically for more of a ranking type of approach to rank and compare differences between your groups. Again, if you use them, you become more familiar and comfortable with them, but you need to understand them. And in our lecture series, we don't get into explaining much more than what I just did. You'll need to find what you will use for your studies to achieve your goals, and then be able to justify your approach and defend your experimental design and statistical analyses. The sequential application of trend tests in a dose-response study. This is from our Selwyn 1995 textbook. I challenge you to find a study in our area of research literature where the trend test is used to test a dose response rather than a one-way analysis of variance with one of these post hocs as a follow-up. So there might be more that scientists should be doing in our area of research. You probably could find this test more commonly used in human subject research where they're doing dose studies, or maybe the subhuman primates to get substances through the FDA and on out to be tested in the clinical setting before becoming available for humans. But I put this in here because it is a test that is supposed to be used for a dose-response study, but we will find ourselves, as I do, using the analysis of variance in either Student-Newman-Cool's or Tukey's to evaluate as the post hoc tests. So the nature of the test for differences between several sample means, the Fisher's F-test is the one used here, not the F-test that we talked about for comparing the variances or testing for equal variances for two groups. This is designed so that it will test for equal variances for more than two groups. So it's based on the fact that the mean of a sample of size n from a normal population with a given standard deviation is itself normally distributed within the variance divided by the n. So again, it's always coming back to the appreciation for and assessment of the true normal population, and we're only dealing with normally distributed data in these discussions. We will talk about non-parametric for data sets that do not pass the tests for normal distribution. But we're always going back to that, and we know that whenever we're thinking about our sample and relating it back to a normal population, the actual population, we're using the best possible approaches to control bias. And then we're analyzing the variance, so we're working with both bias and precision and trying to secure our measures for evaluating the accuracy of our data and our comparisons. Okay? Dirty data produces dirty results and useless conclusions. Good, sharp, crystal clean, and I don't like to use the word clean, but you know what I mean, data gives us the assurance, the credibility for the highest level of stringency and validity and accuracy of our data. If then we have M samples and their means have a greater variance than would be expected from M individuals from a population whose variance is the variance divided by that sample size, we conclude that very probably there are some real differences between the means. So here we're talking now samples when we were talking about groups before. So these are our treatment groups. So N is the sample size for each sample. M is the number of samples or groups that we have. So we have that, say we have 3 of them, and we have 3 means that have a greater variance across the treatment groups. And therefore, you know, and again, if the sample or population variance is represented as this, and this is where we see the lowest variance, and it's across our samples that we see the highest variance, then the source of the variance is due to the treatment. Okay, this is the way of thinking about this. If this is too high, if the variance from within your sample, your treatment group is too high such that it counterbalances the variance across your treatment groups, then you don't have clean enough data when it comes right down to it. Okay, and this is you know, responsibly and validly clean data, obviously. The standard deviation, the variance, not usually known, is not usually known, so you have to estimate the variance within the sample. So we understand this all the time when we get to the point of seeing the population variance and knowing that we're working with samples. We have to estimate get a best estimate of the population variance from the samples. So here's the first time that we'll take a look at this flow chart for choosing a test. And the questions we have on the left-hand side go from 1 to 5. What type of scale? Is it a normal distribution? What are the number of treatment groups? Is it paired or unpaired? Are their variances equal? And then we flow down through. So we have, as we recall, the continuous, ordinal, or discrete data. Let's not worry about these now, because if you have either of these two types of data, you're performing a non-parametric analysis. We're not dealing with that at this time. We are dealing with parametric analyses that apply to normally distributed continuous data. If you have continuous data that is not normally distributed, you have to come over and most often use a non-parametric test. Then we need to ask how many groups. 1, well then you might just do a correlation. 2, then you have to ask, is it paired or unpaired? If it is paired, then you do the paired t-test, and we discussed this in lecture 7. Or was that 8? Well, you just viewed it, so you correct me. I'm losing track here. But in a prior lecture, we talked about the paired t-test, and we discussed paired versus unpaired comparisons. So if you have separate treatment groups from which you're collecting the data, a separate control group, a separate group for this dose of the drug and that dose of the drug, or a combination of the drugs, then you have an unpaired comparison. If you're collecting all your data from the same samples, then it would be a paired comparison. Where I am at a level of challenge right now on this is the example that we used in the lecture was placing different boxes of seedlings in the same environment, exposing one to electricity and the other one not to electricity, and that was called a paired comparison. As I consider my own work, working with cultured cells, they're in the same incubator, and one cell culture is exposed to something and the other is exposed to the vehicle or to the control solution. Is that a paired comparison? I typically treat it as an unpaired comparison because I may have different parameters otherwise, and I'm using separate cultures to generate each data set. So these are things that you need to work out on your own for your own experiments. If you feel you need to consult with a statistician, try to find a biostatistician that has experience working with biological experiments, and you will be most successful. If it is unpaired, you have to ask whether you have equal or unequal variances. If you have equal variances, again, this is just with two groups, you can use the unpaired T pooled variance or an unpaired T separate variance test. So the list of statistical tests grows and grows, as you can see. If using more than 2, then this is where we are now, and you have equal variances, then you use the analysis of variance. So the analysis of variance produces an F-test value that is testing for equal variances, as we saw in the F-test that we described in that lecture. I couldn't remember the number of there. So if you do have equal variances, you can determine this really as you're going through the ANOVA. If you get a significant ANOVA, then you have to choose an appropriate post hoc test. If they are not equal, if you don't pass the ANOVA, then there is some possibility of performing other approaches and still having a valid statistical test, but you might be best to go back and reevaluate your experimental design. You may have to repeat your entire experiment because by the time you get to this point of asking these questions, testing for normal distribution of your data, you at this point are going to be calculating mean and standard deviation, maybe mean, median, mode, and your quartiles, your percentiles, and confidence intervals, and all those types of descriptive statistics. So if you are going to exclude data, you will have done it before you get to this point, either before collection and analysis or after collection and analysis, as we have described in previous lectures. Only valid approaches, of course. So let's take a look at the layout of the design. It's not so much the design, it's how will you put your data into a spreadsheet such that you can feed it into your statistical analysis software package. That's probably the question more of us, or most of us, have to deal with. What do I put in the rows and what do I put in the columns for my particular statistical package to perform a one-way analysis of variance? If you don't put the numbers in your spreadsheet correctly or your data table correctly, you'll still get results. It'll run the test, but it may give you values that make no sense. And this is where you will want to perform some calculations, especially the calculation of the mean and the standard deviation within each of your treatment groups, so that when the outcome or the output of your software is available to you, you can make sure that it calculated the same mean and standard deviation for each of your treatment groups that you did independently, either by hand or with some other spreadsheet function. You have to spot check your statistical analyses along the way. If the mean and standard deviation are different from running your software package for a one-way ANOVA with your post-hoc comparisons than what you did in, say, your Microsoft Excel spreadsheet, you know that one or the other is wrong and you have to rectify this. So the observations of M samples classified one way, we see that we have a treatment or test factor at the level with different levels, and here we see level 1, level 2, out to the mth level. And the mth level, this means it's more than 3, so these are your treatment groups. And then, so those are your columns, and then your observations, your replicate observations out to the n. So if you had 5 data points, or let's do 4 because we've got 4 little spots here, data points for each treatment group, it would be the X is the individual observation, as you recall, the data point for level 1, treatment group 1, and that's the first observation. X sub 1, 2 is the second observation of the first level, and third and fourth, on out to the X sub 1 to the nth. So it's important to go through this to get that feel for what the n is representing, our sample size or our group size, our treatment group size. And then we notice as we go across, we end up with xm sub 1 all the way down to x sub mn. And so this is the mth treatment group and the nth observation within the mth treatment group. So if it's our 5th treatment group and our 5th observation, then that data point goes there. And there are 2 calculations that are generated from this data table. There is a grand mean and then a column mean, or the mean for each of your groups. So the one-way ANOVA is going to calculate the mean for each of your groups, and this is the number that you will be provided in the output table, your ANOVA table in the end, results table, that you use to compare back to your own calculations independent of the software package. Again, I'm assuming that everybody's using a software package. If you're doing it manually, God bless you. And obviously for each treatment group you're going to calculate a mean. And ultimately a standard deviation and a standard error of the mean, and it's these means, once you've verified them, and your standard error of the mean that you would put on your graph, line graph or bar graph, or however you might be graphing it. And then a grand mean will be calculated as well, which is the x bar equals x bar 1 plus x bar 2, so the sum of the group means divided by the total number of treatment groups over M. So you can see we're beginning to get an assessment of the mean for each group and the mean across treatment groups and standard deviation and variance, and we're beginning to examine how much variance is there around this measure of central tendency versus variance, in this one and this one out to the mth, and how much variance is there across our data points. And we'll see that it won't matter how you put these numbers in. You can put this one up there and that one down here, and it won't affect this mean, and it will not affect the grand mean either. Okay, but you cannot change columns. You can't take this number and put it over here and this number and put it over here. So we'll see how that has impact on determining whether you have a one-way or two-way analysis of variance. And I guess I should say you can't take this number and put it there and take this number and put it there without predictably having some effect on the evaluations of the rows versus the columns. So the xijth may be coded by subtracting a from each of them. So let's not worry too much about that at this time. We'll see that popping up later when we discuss things in more detail. So here's an example. The dye color with the treatment level, 4 different dyes. We have one control, the undyed material, and the observations, 3 observations on each. So we have our 4 columns and 3 rows, or I guess I should say 4 columns and 3 rows, and the mean for each column 111, and the grand mean 105.5. So from the tabulated data, we note the use of the general term treatment instead of dye, so our different treatment groups. Each dye is referred to as a level of a particular treatment. Remember, we are using test factors, so we have one factor at different levels, so we have a one-factor analysis or a one-way layout experimental design, and the levels are greater than 2. The jth observation at the ith level of the treatment is denoted as x sub I j. So whatever level, it'll be out to m. M is the statistical code that we use for it, but I is telling us treatment group, the different levels, and J is the number of replicates that we use, replicate observations or data points within each treatment group. So Xij would be your 10th observation in your 20th treatment group. Good God, don't study that many treatment groups all at once. You have to go on to other tests probably because you just have too many comparisons that you're making. So let's just say the 4th treatment group. So the 10th observation in the 4th group, and the n value would be the 10, and the m value would be 4. Hopefully I said 4 treatment groups there. Shouting out too many numbers and losing track of them all. So the levels may be numbered in any order. So it doesn't matter how you arrange your columns, as long as you don't mix and match your observations. You don't get your I's and J's all mixed up. Right? So you can put your control group at the end, or your control group first, and then it can be blue and then red. Doesn't matter how you organize these columns as long as each column is moved all collectively. Oh, hit another button there. Okay. So the observations in a single column may be rearranged in any order, as I said, but that the observations in a single row cannot be rearranged without altering the means. So you can't take a data point from one row and move it 3 rows down because it would change the means. So that's quite obvious to us, but here if we took this 108 and switched it with the 100 over here and put the 111 there, obviously we're going to change our column means and maybe not impact our rows too awfully much. In other words, we're just disorganizing the data, so we know our outcome is not going to make any sense. So that means it's a one-way ANOVA. Since the observations are said to be classified in one way only. You can only move the columns, but you can't move individual, you can move any numbers across rows within the column, but you can't move any numbers along a row from one column to the next. So you can only move them one way without changing the means, and that's a one-way ANOVA. A one-way layout, that's your experimental design, so you use a one-way ANOVA. Let me be more specific about that. So the treatments, very generally, they are the observations that are counts of the number of tomatoes. For example, on each of N plants selected at random, from each of M varieties of tomato plants, then each variety is a different treatment level. So I know these are not the most, unless you're doing some type of plant study such as this is not what we're most commonly working with, but it provides us an example to see how there is an experimental design laid out in the one-way layout for a one-way ANOVA. So the observations are analyses of the product of a factory, as another example, and analyses being made each day of the week to see if there is variation from day to day, and then the days of the week are the treatment levels. So we're making a single observation on a product each day, excuse me, single observations on a product each day. Observations on single products, single individual products each day, and different selections of those, the same product day after day. So if it's nuts and bolts or just the bolts, you're looking at a different set of bolts on day 1 than you are on day 2. And the reason I'm trying to be very careful in explaining that is that if you're looking at the same one day after day, that's a repeated measures design. So you have to be careful when you're looking at a day-to-day or temporal measurement, whether it's different levels or if it is a repeated measure, because it will be different, as we will see. In this case, you're looking at different sets of the product, same product that they're trying to sell, merchandise, but different sets each day, a certain number of them each day, and therefore each day is considered as a potentially different level of your test factor. And am I producing the same stuff every day? So you can see these can become pretty challenging. Do I have a repeated measures one-way analysis of variance because I'm measuring over time, or do I have a one-way analysis of variance because I'm making this single type of an observation, but once at different time points? So you have to work on that and seek assistance if you can't work it out, and make the determination on your own. Each treatment level may differ qualitatively from the others. They may be blue, green, red, etc., dyes of different chemical composition, and they are not necessarily different quantities of the same dye. So now let's get into some of the formula. And again, we're not trying to be experts in memorizing or learning formulas, but and I'd love someday to test you on these, but we won't worry about that for now. Might ask you to recognize some of these formula in the quizzes on these, but we'll see how that turns out. So we test for the difference between means of samples of the same size. So if you don't have the same N for each M treatment group having different sizes, then you can run into some troubles in running these types of evaluations. You calculate the mean of each column, the grand mean of the means, and then you have to get the estimates of variance. So we said that we were progressing from calculation of means to the calculations of the variance. So remember that variance was the sum of the mean squared differences. So the sum of the mean squared differences over the degrees of freedom. Now what we see is the S prime squared equals the differences between each column mean, each treatment level mean, the mean for each treatment group, and the differences between that and the grand mean of means squared. And notice, I hadn't mentioned this previously, what we accomplish by squaring this is that if we get a negative number, it becomes a positive number. So we're always dealing with positive numbers when we're talking about standard variances. So it's always a positive value. So x1, x2, and so on and so forth, divided by the degrees of freedom for the across the columns, m minus 1. So how many columns do we have? And then we get the degrees of freedom, so obviously that. S prime prime squared equals x1 sub 1 minus the mean for treatment group 1. So here what we're seeing is we have treatment group 1 where we're getting the mean squared differences, sum of the mean squared differences. Am I pronouncing that? Am I stating that correctly each time? For each of your treatment groups, and this is the variance for the rows. So we're getting the variance across the column for the columns, and the variance for the rows. So you can look through this, and if you remember any of your calculus, how this works. Anyway, finally, the denominator is m times the n minus 1. So this is why you have to have the samples of the same size, because the n will be the same for all of them. So when you do n minus 1 times the number of treatment groups, it will be accurate. If you have unequal sample sizes across your treatments, then this is going to be an inaccurate calculation. What number do you use? The largest n, the smallest n? So you can see the challenges there. So here on the lower right hand side is a teeny tiny table that you can't really see, but basically it's that table that we saw on the previous page. We're getting an estimate of variance across the columns and an estimate of variance, total variance across or down the rows. So we test for the differences between the means of the samples of the same size. We understand the significance of this part now, since the S prime squared is an estimate of sigma squared over n. So the variance of the columns is an estimate of the population variance corrected for our sample size with m minus 1 degrees of freedom. We saw that. That is n times S prime squared estimates sigma squared with m minus 1 degrees of freedom, and the S prime prime squared, the rows variance across of the rows is an estimate of sigma squared with m n minus 1 degrees of freedom. Therefore, we calculate the test function, the Fisher critical F test for analysis of variance, is, again, a ratio of the variances. Remember, that's what we saw before, but this one is slightly different, where we have this two variances calculated in different ways. We have the variance of the columns divided by the variance of the rows multiplied, of course, at the numerator side by your sample size. And therefore your sample size has to be the same. Again, we come back to this, if the observed S is greater than the critical F with degrees of freedom 1 of m minus 1 and degrees of freedom 2 of mn minus 1, at the desired probability level, we conclude that some, at least, of the treatment levels, treatment groups, are causing significant variation. And this is the whole point that's being made here. The source of our variation should be caused by our treatments and not by the data within any one treatment group. And this is the way that the stringency is increased in an analysis of variance when you have more than 2 treatment groups versus the level of stringency, although acceptable if you have only 2 treatment groups, of the t-tests that we had noted before. So again, our table is here, and so we have m equals 4 and n equals 3, so the variance for the columns equals minus 3.5 squared, minus 0.5 squared, minus 1.5 squared. So notice that these become positive values. All divided by 4 gives us 11.2. And then the row variance comes out to be 3.78. I'm not going to read all the numbers in the formula for you, obviously. Hence, F equals 3 times 11.25 divided by 3.75 equals 9, which is greater than the critical value for F, V sub 1, which is 3, and V sub 2, which is 8, equals 7.59. So 9 is greater than that at a 1% level, so we'd go and look at a table for this. So there is a significant difference between the sample means here. Now, the reason for showing you this is that when you report the outcome of an analysis of variance, this is the format, part of the format in which you report it. You would state in your results the analysis of variance was significant, and then in brackets, in little square things, you would put F, open parentheses, the degrees of freedom for the treatment groups. Okay, that was the M minus 1. And then the degrees of freedom total, which was the 8 shown here. So you obviously don't put the V sub 1 and the V sub 2. You'd put F open parentheses 3 comma 8 equals 7 point, well, it would be equals 9. You would be reporting your observed F value. And then you'd put a semicolon after the 9 that would be here. P less than, let's see, 1% is 0.01, 0.01. So if the observed F is significantly large, you then can test each individual sample mean against each of the others using a post hoc. And again, they put the t-test here, and I strongly advise against using the t-test. Use one of the others that was mentioned for significant differences between the groups performing a pairwise comparison. So you must pass the ANOVA test before you can go on to comparing your treatment groups. So you look and you go, wow, 102, 105, 104, 111. You know, these may not be significantly different from each other, but this one's got to be significantly different from something else. That's great to do some estimating like that, but you really don't do your comparison of these statistically until you run your analysis of variance and calculate your observed F value and compare it to the critical F value. If you exceed that, then you are significant, and depending upon what level you look at, the critical value will differ depending upon the level you look at. So it'll be easier to surpass the 5%, harder to pass the 1%, even harder to pass the 0.1%, which would be p less than 0.001, right? So you get the picture there. So again, this is evaluating continuous data that is normally distributed, more than two groups with equal variance, and we have passed the analysis of variance. It is significantly different. F open parentheses 3 comma 8 equals 9 semicolon p less than 0.01. We passed at the 1% level. There is significant differences due to the treatment, but we can't tell you exactly which treatment is different from any of the others, so we now have to do a post hoc test to follow up on that. And again, I'm assuming you just select that in your software package, and we should be able to reach the point of showing the example that I have in the lecture set here. So the one-way ANOVA, when there are two or more treatment categories or conditions, or a more general formulation of a normal theory test is provided by analysis of the variance. In the ANOVA framework, an overall null hypothesis is that all treatment means are the same. Whereas in the alternative hypothesis, this is the statistical hypothesis, you're recognizing our type 1, type 2 errors here, we postulate that at least some means will differ. So if we reject the null hypothesis, then we accept the alternate statistical hypothesis, and we conclude that some means differ from the others across the treatment groups. If we are dealing with a multi-factor experiment, such as a full factorial design, then the overall difference among the treatment conditions is partitioned among the various factors and their interactions, called a source of variation. The analysis of variation is a global method for eliciting differences among those treatments, and depending on the specific treatments in the study at hand and their correspondence to one another, other methods of analysis might be preferred even when normal theory methods apply. So we saw that there's that little dashed line that might take us someplace else to look at our data from other approaches. There are several examples that will help to illustrate this idea. Suppose, for example, that we have conducted a study in which one of the treatments is a control or standard to which each of the other treatment groups is to be compared. In this case, multiple comparisons with a control or standard, here Done It and Dunn published this, will be preferable to ANOVA as they have been designed specifically for that particular type of purpose. Similarly, if the goal of the study is to focus on specific comparisons, such as all pairwise comparisons in the study, or even just a selected set of them, then other methods of multiple comparison will generally be superior to the ANOVA. So these are post hoc tests. Tukey's honest significant difference, the Tukey test I mentioned to you, that is more stringent than the other ones that were listed, such as the student Newman-Cools. And the Bonferroni method of adjustment for multiple comparisons. So there is an approach if you're getting a little bit past 4 or 5 treatment groups and therefore comparing all of those to each other, there's a risk of error, getting false positives, so you will want to make some type of a correction. You may want to visit with a statistician. So the ANOVA for one-way classified samples of equal sizes then, if sigma squared, the variance sub B is the variance of levels across the columns, and the sigma squared is the variance due to all other causes, the rows, then sigma prime squared, or S prime squared is an estimate of the sigma squared sub B plus sigma squared over N, which is the variance in columns as affected by the rows, with M minus 1 degrees of freedom, and the S prime prime squared is an estimate of sigma squared only, with the Mn minus 1 degrees of freedom. We then test the hypothesis that sigma squared sub B equals 0 by testing N S prime squared divided by S prime prime squared, which equals the observed F against the critical F, with V1 equals M minus 1 and V2 equals Mn minus 1, our degrees of freedom. So in hearing that read to you or reading it yourself now, it should make a little more sense. Okay, if you just open a book and read it, it might seem quite odd, as it did to me when I first read it. And so hopefully our discussion is making this clearer to you, why you have to perform an analysis of variance and what it accomplishes. If the observed F is greater than the critical F with degrees of freedom 1, M minus 1 treatment, and V sub 2, the total degrees of freedom, at the desired probability level, we conclude that the sigma squared sub B cannot be 0, and we estimate it from the formula. We reject the null hypothesis, what you're seeing there. So we use this formula. It's the same one we've been talking about. Oh no, I'm sorry. Should have looked more closely, getting focused there. The estimate of sigma squared sub B equals the treatment, the variance of the columns minus the variance of the rows divided by the sample size. If observed F is not significantly larger than sigma squared sub B, then we can, if observed F is not significantly larger than the critical F, then this can be neglected, and the theoretical best estimate of sigma squared is sigma sub B squared in practice. So in other words, it is telling us that the variance across the columns due to the treatments is the largest source of the variance. And look, the variance due to the rows is even divided by, it's reduced by the number of observations. So if this becomes so large that it critically affects this value, then the variance within your treatment groups, the rows down in the columns, it's all taken into account as we'd seen, but basically you can think of it as one or more of my treatment groups has so much variance across its data set that it's made this number so big that it compromises the contribution of the differences between my treatment groups. So there's something wrong with the experimental design. Or there isn't enough difference within your treatment groups. You might have a nice tight variance, but you might not have a big enough variance across your treatment groups, your columns, to push this number up to be able to conclude that even though your experimental data sets are nice and tight, you don't have enough differences across your treatment groups to believe that there is an effective treatment. So this is how it works. It not only looks at your dispersion of data around the mean within each treatment group. If that's good, if you've got nice accurate data in each treatment group, then it is what weighs more heavily is just how much difference might you have among all of your treatment groups. Is there any one of them that generates enough difference, or a couple of them that generates enough variance when you compare across your groups to say that one of them must be significantly different from one of the other ones at a minimum, and therefore you have a significant ANOVA. Go on to a post hoc analysis and find out which ones differ from each other. So the one-way ANOVA compares 3 or more, in discussing the p-value, 3 or more unmatched groups based on the assumption that the populations are Gaussian, so it's only for normal data. The p-value answers this question if it's significant, right? If the populations really have the same mean, what is the chance that random sampling would result in means as far apart, or more so, than observed in this experiment? So again, that's saying, are the means that I have observed in each of my treatment groups reliable, or are they generated by some peculiarity within the data set that that belongs to that mean? Right, so the frequency curve for each of our data sets becomes very important. Is it nice and tight up around our mean? Not too tight, but not too loose either. So do we have, and does that mean represent the true population mean for that condition under that treatment? So do I have my bias under control? Do I have my variance under control? If so, is it an accurate representation of my mean? Well, and the program that I use, it's called the PRISM program. I've shown you this once before for the estimate of the sample size and the power analysis. A Bartlett's test for equal variances is run. So let me read through this so you can understand what this contributes. It's based, the ANOVA is based on the assumption that the populations all have the same variance. If your samples have more than 5 values, then this software package tests this assumption with the Bartlett's test. It reports the value of this statistic and the p-value that answers this question. If the populations really have the same variance, what is the chance that you'd randomly select samples whose variances are as different or more different than observed in your experiment? So the Bartlett's test is very sensitive to deviations from a Gaussian distribution. So again, it comes back to that curve. Is it a real nice bell-shaped curve? If it deviates from that, then your Bartlett's test is going to be weakened. So the Bartlett test is very sensitive to deviation from the Gaussian distribution, more sensitive than the ANOVA itself. A low p-value from the Bartlett's test may be due to data that are not Gaussian rather than due to unequal variances. So if you don't pass a test for normalcy, you can't run a one-way analysis of variance. You have to evaluate your true data distribution. Is it skewed to the left or right? Is there a kurtosis or whatever might be different in your frequency distribution? You have to account for it. If it is due to experimental problems, you've got to repeat the experiment, fixing those problems, getting new data sets. That's the legitimate way of doing it. If not, you have non-parametric data, you have to go and analyze with non-parametric evaluations. I'm not going to bother with this final paragraph there or this page. I want to make a couple more points before completing this lecture. So in the ANOVA table, you get a p-value. It's calculated from there. The key idea is that variability among the values can be partitioned into variability between group means and variability within groups. So the variability within groups is quantified as the sum of the squares of the differences between each value and its group mean. We saw that calculation. This is the residual sum of squares. The total variability is quantified as the sum of the squares of the differences between each value and the grand mean. This is the total sum of squares. So since we've looked at these formulas before reading these, hopefully you're picturing those formula as this is being read, those formulae. The variability between groups have to have some jocularity in this because most of us probably end up clicking our buttons on our statistical packages and we're not thinking about this anymore. So this is an important time to think about it and just becomes a bit comical to me. Forgive me. So the variability between group means is calculated as the total sum of squares minus the residual sum of squares. This is called the between groups sum of squares. One thing I do know is that I rarely encounter discussions among graduate students and researchers in the hallway that sound much like this. So it is a bit funny to me. Anyway, it's dead serious, as we know, and we don't take it lightly. We just appreciate interdisciplinary differences, especially in jargon and the way that we word things. So I guess our discussions, our writings sound that foreign to statisticians, right? So if you have to consult with a statistician, find one who is experienced in biostatistics, and best if they're experienced with a particular type of experiments that you perform. So even if the null hypothesis is true, you expect values to be closer on average to their group means than to the grand means. So within any one treatment group, the means are distributed within there, right? So any value that you would take from samples treated that way should fall somewhere within that data population set, not within one of the others, is what's being stated there. So the calculation of the degrees of freedom and the mean square account for this. See a statistical book for details. Good advice. The end result is the F ratio. If the null hypothesis is true, you expect to have an F. You expect F to have a value close to 1. If F is large, the p-value will be small. So this is why we exceed the critical F value with our observed, and we get a significant difference. So here is an ANOVA table. You get the source of variance between samples, within samples, total. Here are those formulas we talked about. Well, we saw them represented, the sum of squares here for between samples, within samples, and the total. And of course, those are divided by these to get the column variance and the row variance and the standard deviation estimates are shown over here, as we had said. So this is the general layout from a theoretical perspective. It seems theoretical to me, maybe very practical to a mathematician, for what we would see when our software gives us our results. So in words, the sum of squares between samples and within samples add to give the total sum of squares. The same is true of the degrees of freedom. Add this and this, and you get this. I'm not going to worry about this right now. What I'm going to do is jump ahead. I'll leave the other for you to read, and I'll probably pick it up in the second portion of this. What I wanted to do at this point was to show an example in the last few minutes. So again, this is the Prism GraphPad software that I use in my experiments. I gave you that source in the prior lecture. I like it because you can see up here you have the little tabs. There's the data tab. You can put your data in here in a variety of table formats. You can do an analysis. You have a results tab. You have graphs that are made automatically. You can modify them very easily. You can put your graphs and tables into a layout, capture these layouts, and they go right into your report or your publication or your PowerPoint presentation or for your poster. And all of your experiments are contained right in here. You can have notes on each lecture. One file can be your whole dissertation, which you back up and archive on a regular basis. It's a wonderful software package. I'm not trying to sell it to you. I just really want to express my appreciation of it. So here are three different treatment groups. This was a study where we were testing a neurotoxin in combination with a drug that inhibited the degradation of neurotransmitters, monoamines. So we had our vehicle group, our neurotoxin vehicle group, and then our neurotoxin inhibitor groups. So we had 3 treatment groups. Yes, there is another group that's missing. It should be the 0-3 group. I now have completed that since then, and we have the complete set of results. But anyway, to analyze these for these purposes, we can see that when I ran the test for the one-way ANOVA, it's a one-way ANOVA, the table that was analyzed was the area density data table. So we go over here and look for it. That's what it would be titled as. We have a p-value shown up, so you want to look at this first. This is p less than 0.0001, so this is the 0.01% probability, so that's very significant. And obviously, are the means significantly different? Less than the preset 05? Yes, of course they are. We see that immediately. Number of groups, here's the F value, 34.5. So if I was going to report this, the ANOVA was significant, open parentheses, or open brackets, F equals open parentheses, come down here to the degrees of freedom for the treatments. It would be 2, the M minus 1, and then the total is 14. So it would be F open parentheses 2 comma 14 close parentheses equals 34.5 semicolon p less than 0.0001. That's how you report your results for an analysis of variance. This is significant. If it was not significant, sometimes you show your F values just the same. And as people become more and more familiar with statistics, and if you get a reviewer who's really familiar with it, they can look at all of these compared to the experimental design that you described and determine if you've made a valid test. And then down below here it shows the results of the Newman-Cool's multiple comparison test. So it compares each treatment group to the other and gives a p-value less than 0.001, less than 0.01, less than 0.01. And then you can also have up here, you can select it to show the column statistics. You can get the mean, standard deviation, standard error. It gives the number of values, your n, maximum, that's minimum, maximum, median. Doesn't provide the mode. Gives your quartiles, 25th and 75th, and the lower and upper 95% confidence intervals. So you get all this information. It's a very nice package. You come to your graph. It graphed it for me automatically. And I've got my 0, 0, 10, 0, 10, 3. You see the means. So you see the effect size, the standard error of the mean that was on our prior data table there. So this is the standard error of the mean that was I selected that one to be put on the graph. So you see that those are pretty tight. So even with a small n, this is very tight data. Not too tight, but tight enough. And we got a significant ANOVA, as I reported to you, the F value and the P value. And the student Newman-Cool's post hoc multiple comparisons test showed that comparing it to vehicle, the 2 asterisks by standard, typically 1 asterisk is P less than 0.05, 2 asterisks is P less than 0.01, and 3 asterisks is P less than 0.001, and that's compared to the vehicle and to the this treatment group here, as was shown from the statistics table. So I'll cover some of the slides that we zoomed past in the next lecture, and then continue on to talk about a one-way ANOVA with repeated measures on time for the second half of the lectures on this slideshow. Thank you very much for your time and attention. Bye-bye.